Hello everyone, welcome back to my channel. Today we would be solving the paper 3 of Math AAHL of the November 2021 attempt. So let's start with the first question. So overall in this question there are two big questions with subparts. So let's start with question 1. So in this question 1 we have functions f and g, and they are defined as fz equals e to the power z plus e to the power minus z whole divided by 2, and gz would be e to the power z minus e to the power minus z whole divided by 2, where z is a complex number. So yeah, consider t and u such that t and u belong to R. So t and u, these are real numbers, or they belong to the real domain. So you have to verify that u equals ft. So let's say we replace the z with t. So the differential equation dtu by dt square equals 0 is satisfied. Let's try to solve this first part. So ft would be equal to e to the power t plus e to the power of minus t by 2. This is the value of ft. Now this is equal to u, basically u equals ft. Now we have to find out du by dt and dtu by dt square. So du by dt would be ddt of e to the power t plus e to the power of minus t divided by 2. It would be half would come out, so we have a normal differentiation. So ddt of e to the power t is e to the power t, and ddt of e to the power minus t is minus of e to the power minus t. So this is the value of du by dt. Now we have to find d2u by dt square. So we have to differentiate du by dt again with respect to t. So this means we have to differentiate this. It would be half of differentiation of e to the power t with respect to t is e to the power t, and differentiation of e to the power minus t with respect to t would be minus of e to the power of minus t. If we simplify this, we'll get e to the power t plus e to the power of minus t. So we can compare this and this. They look exactly similar. So d2u by dt square, I missed a 2 here. Yeah, d2u by dt square is exactly equal to u. So yeah, it is verified. It's verified. That is all about the part A of this question. Now let's try to do part 2. So part 2 goes like this. We have to prove that ft square plus gt square, that is equal to f of 2t. So first let's find out f of 2t. This was f of t, so we just have to replace this t with 2t. So e to the power 2t plus e to the power of minus 2t by 2. This is f of 2t, and we have to show that ft square plus gt square will be equal to f of 2t. So ft square would be equal to e to the power t plus e to the power minus t by 2 whole square. This would be 1 by 4, and a plus b whole square is a square plus b square plus twice ab. So e to the power t times e to the power minus t, this will become 1. So I can write ft square would be 1 by 4 e to the power 2t plus e to the power of minus 2t plus 2. I guess I can write that. Similarly, I can write gt whole square. Gt would be e to the power t minus of e to the power of minus t by 2. We have to square this term. So yeah, the bottom two would become 1 by 4. Then a square minus b square is a square plus b square minus twice ab. Again, e to the power t times e to the power minus t would be equal to 1. Now we have to find out the sum of ft square and gt square. This would be 1 by 4 e to the power of 2t plus e to the power of minus 2t plus 2 plus 1 by 4 e to the power of 2t plus e to the power of minus 2t minus 2 will be divided by 4. So let's take out 1 by 4 as common. So we will have e to the power 2t plus e to the power of minus 2t plus 2 plus e to the power of 2t plus e to the power of minus 2t minus 2. Upon simplification, might need a ph here. Yeah. Upon simplification, we will find that it reduces to twice e to the power of 2t plus twice e to the power of minus 2t. So I can just take this 2 as common and divide it with the denominator. So we will be left with, this is the final value of ft square plus gt square. Now if I just compare it with f of 2t, which I found out here, you'll see that this is exactly equal to f of 2t, which I found out at the initial part of this question. So ft square plus gt square, this will be equal to f of 2t. Verified. Now comes the part C. In part C, we have e to the power. They have already given us this relationship that e to the power iota u can be written as cos u plus iota sin u. So we have to find the expression in terms of sin u and cos u for f of iu and g of iu. So again, f of z, this thing was e to the power of z plus e to the power of minus z by 2. Now we have to find out f of iu. So let's put iu in place of z. So e to the power of iu plus e to the power of minus iu by 2. Now let's just convert it to our normal equation. So first one would be cos u plus I sin u, plus this one would be cos of minus u plus I of sine of minus u divided by 2. So I can write cos of minus u as cos u, because cos eats up the negative sign, so we can have 2 cos u. But for sine, the negative sign comes out of the sign and it becomes minus of sine u. Finally, I can write f of iu as cos of u. This is the answer to the first part of the question. Now we have a second part which we need to solve. Let's try. We have to find out g of iu. Firstly, let's write what's gz. Scrolling up, we have our gz here. So gz is e to the power z minus e to the power of minus z by 2. This is gz. So we have to find out g of iu. Let's replace z with iu here. E to the power iu is cos u plus I sin u, minus e to the power minus iu is cos of minus u plus I of sine of minus u divided by 2. Now g of iu again would now become cos of u plus I of sine u. So cos of minus u would become cos u, because cos eats up the negative sign, while I sine of minus u will become minus of I sine u. So if I open the brackets and perform some calculations, you will find that the numerator becomes I sine u by 2. So g of iu is basically I of sine u. This is all we were asked to do in this question. Now let's get to part D. We have to find and simplify an expression for f of iu square plus g of iu square. So f of iu square plus g of iu square. F of iu square is basically cos square u. So I can just write it as cos of u whole square. Well, g of iu we found out as I sine u. So I of sine u whole square. So this becomes cos square u plus I square sine square u. Now we know that I square value has a I square has a value of -1. It becomes cos square u minus sine square u. Cos square u minus sine square u becomes cos 2u. And that is the final answer to this question. That is the most simplest expression that's possible. Now moving on to part E, we have to show that ft square minus gt square will be equal to f iu square minus g of iu square. Let's find out the RHS first. So f of iu whole square minus g of iu whole square. How much will it be? F of iu was cos x, cos u, while g of iu was I sine u. Let's just plug in this value. This is cos u whole square minus of I sine u whole square. Now this becomes cos square u, and this becomes I square sine square u. I square has a value of -1, so it would be cos square u plus sine square u. Now we all know that sine square x plus cos square x becomes 1. So even in this case also cos square u plus sine square u will be 1. So the RHS has a value of 1. We have to prove that the LHS also has a value of 1. So we can just say LHS equals RHS, since it's verified. The LHS would be f of t whole square minus g of t whole square. F of t was e to the power of t, e to the power of t plus e to the power of minus t by 2 whole square, minus g of t would be e to the power of t minus e to the power of minus t by 2 whole square. Now we have to simplify these a little bit, and we will get to the final answer. The denominator becomes 2. It becomes e to the power of 2t plus e to the power of minus 2t plus twice e to the power of t e to the power of minus t. Again negative. This part becomes e to the power of 2t plus e to the power of minus 2t minus twice e to the power of t e to the power of minus t. Now upon opening the brackets and simplification, and also plugging in that e to the power of t times e to the power of minus t becomes 1, we find that the numerator becomes 4, the denominator was 4. So LHS also comes out as 1. Therefore we can say LHS equals RHS, hence verified. Now we come to our next question. So here we have the functions cos x and sin x are known as circular function in general, as a general point defines points of a unit circle. Okay, if you put x as cos and y as sin, you will get that x square plus y square becomes 1. So function x and fx and gx are known as hyperbolic function, and in general point f theta g theta defines a point on a curve known as hyperbola. Okay, and hyperbola has 2 asymptotes. In the first question, we have to sketch the graph of x square minus y square equals 1, stating the coordinates of any axis intercepts and the equation of each asymptote. So let's try to find the asymptotes first. For hyperbolas, in order to find asymptotes, there is one really simple method. That is, we have to replace this 1 with a 0. So 1 with 0 in the curve equation, and solution of this new equation will give you the 2 asymptotes. So x square minus y square equals 0. So y square becomes equal to x square. So y will be equal to plus minus root under x square. So basically the axes are y equals plus minus x. So y equals x plus x and y equals minus x are the two asymptotes. So we found out the equation of two asymptotes. Now we have to find out the intercepts and we have to find out the domain. Let's try to find the domain. So x square minus y square equals 1. So y square would be x square minus 1. So y would be root under x square minus 1. Obviously you can have a plus minus in the beginning. So for this now here, for the true domain, x square minus 1 should be greater than equal to 0, because if this value is less than 0, you will have like complex numbers. But if we are working in the real plane, we cannot have complex numbers. So x square minus 1 should be greater than equal to 0, x square should be greater than equal to 1. So x should be either be greater than equal to 1 or x should be lesser than or equal to minus 1. This is the first conclusion. This is the domain. So there won't be anything in between minus 1 and 1. Now the intercepts. Let's find out the x-axis intercepts, because we just need them. So x-axis intercept means y will be equal to 0 at that point. So x square minus y square equals 1, plug y as 1, so x square equals 1. So x will be equal to plus minus 1. So these are the two intercepts on the x-axis. So we are now good to go. We have most of the information which we need in order to draw this hyperbola. So to draw this curve, we actually need to know, like, specifically know how hyperbolas look like. So hyperbolas, they generally look like this. They have these two asymptotes. This is one of the asymptotes. This is this is one of the asymptotes and this is one of the asymptotes. The hyperbolas generally have this type of structure. So we will just use it in this case also. Let's draw the x and y axis. This is the x-axis and y-axis. Let's say this point is 1 and this point is minus 1. Now we will draw the line y equals x and y equals to y equals minus x. Now this is very random, might not be very accurate here. Let's say this is y equals x, and let's say this line is y equals minus x. So our curves will not have any domain between minus 1 and 1. So we can draw it in this fashion. Yeah, we can draw this one as this. And similarly, we can draw the other part too. That's how overall our curve is going to look like. This is y equals to x and this is y equals minus x. This is the hyperbola. And that is the answer, pretty much that's the answer to this part F. Now moving on to the next part. The hyperbola with equation x square minus y square equals 1 can be rotated to coincide with the curve defined by y equals k. So we have to find the possible values of k. Now thing is, this is a hyperbola, of course, and we just found out how the curve will look like. Now xy equals k is also a hyperbola, and here what would be the asymptotes? For xy equals k, the asymptotes will be x equals 0 and y equals 0. So if I try to draw these curves, they will look like this. This is for xy equals k. It looks somewhere like this, and yeah, there will also be one in the third quadrant. And this was for x square plus y square equals 1, which we just found out in the previous problem. Yeah, you have the asymptotes. So from here, we can just say that if we rotate the x square minus y square curve a little bit in this direction or in the anti-clockwise direction, we can actually, coincide this curve with xy equals k. Now, how much by how much angle do we need to rotate it? See here, basically we have to rotate it by 45 degrees, or by trigonometric terms, we have to rotate it by minus 45 degrees. So yeah, x square minus y square equals 1 should be rotated by minus 45 degrees. Now we have a rotation formula which we can directly apply in this problem. So what is our rotation formula? It looks like this: cos theta minus sin theta, cos theta. This is the first matrix, and you have xy. This will be equal to xy. Now let's put the value of minus 45 in the trigonometric term and try to reduce this equation. We have cos of minus 45 minus sine of minus 45. This is sine of minus 45. This is cos of 45. The negative is not here. Basically, the negative is with the sign. Xy equals xy. Now let's try to put the values in here. Cos minus 45 is 1 by root 2. Minus of sine 45 is again 1 by root 2. This is minus 1 by root 2. This is 1 by root 2. Is equal to xy. Now we can just write the equation, or we can multiply these two matrices together. What we get is Now comparing the rows, we can write two equations: x equals x by root 2 plus y by root 2, and second equation is y equals minus x by root 2 plus y by root 2. Now we have the values of x and we have the values of y. From here, we can basically put these two values in the x square minus y square equal 1 equation, and eventually get the value of k, or you can just multiply x and y together to get the value of k. So let's multiply x and y together. Let's see what happens. Plus y by root 2. So this becomes y square by 2 minus x square by 2. So continuing with this problem, y square minus x square by 2, and we know that x square minus y square equals 1. This relationship exists, so I can also write it as xy equals minus 1 by 2. This is one of the solutions, and there is another solution that can be possible. So x square minus y square equals 1. This was the previous equation, so I can plug in the values of x and y in it to get the new equation. So x by root 2 plus y by root 2 whole square minus y by root 2 minus x by root 2 whole square equals 1. Here we get x square by 2 plus y square by 2 plus xy, minus we will get y square by 2 minus x square by 2, and again we will get a plus xy equals 1. Upon cancellation, we will find xy as half. So xy can either be minus half or xy can either be half. So k will be equal to plus minus 1 by 2. This is the answer to this question. Moving on to the next question. Here we would be here you will be exploring strategies required to solve a system of linear differential equations. So we are given two differential equations where x, y, t, these belong to the positive real domain, while a is a parameter. Now they have given us cases where a equals 0, then we will have case where a equals minus 1, etc., etc., and using these cases we have to solve the differential equation in each case. Let's start with the first one. So first one, a is equal to 0. So we have to solve the differential equation dy by dt equals 5 and show that y equals a to the power a times e to the power of t. So this is a t. So let's try to solve this. What happens is dy by dt equals y. Just a basic way of solving the differential equation. Now we have to integrate both sides. What will be here dy by dt, integral of dt. So integral of dy by y gives us ln of y, and integral of dt gives us t plus c. So yeah, so I can just write it like this: y equals e to the power of t plus c, can also be written as e to the power of t times e to the power of c. Then I can just assume where c is the constant of integration. Yeah. Another thing is we can just assume e to the power c as c. This is another constant. And what happens is y becomes a times e to the power of t. This is what we need to prove in this question, and yeah, we have successfully proven it. Now in the next part, we have to show that dx by dt minus x is equal to minus a e to the power of t. So we have another equation, dx by dt equals x minus y. This one is pretty simple. Just write the initial equation and plug in the value of y, you will get the answer. I'm bringing the x to the left hand side, and this is minus y. Minus y we have already found out, it's a times e to the power of t. So yeah, that's what we need to prove here. In the next part, we have to solve the differential equation in part A2 to find x as a function of t. So we have to just resolve this differential equation. So dx by dt equals minus x equals a to a e to the power of t equals minus a e to the power of t. That's what we need to solve, I believe. Yeah. So here this is basically a linear differential equations. So we can just compare it with dx by dt plus pt times x is equal to qt. If you just compare, you will see that pt is equal to minus 1, which is a constant, and qt is equal to minus a e to the power of t. Now yeah, we have to find the integrating factor. Integrating factor is integral of a to the power of pt dt. So this is the integral of e to the power of minus dt. This becomes e to the power of minus t. This is the integrating factor. Now what is the solution to this differential equation? It would be 1 by it times integral of it qt dt plus c. Now we are more or less done. Just we need to plug in the values and evaluate this integral. So 1 by this would be e to the power of minus t xt. Integral it is e to the power of minus t, qt is minus a e to the power of t dt plus c. Yeah. What happens? This will become e to the power of t, and this will be minus a integral dt plus c. C is another constant of integration. Yeah. So finally what we are left is e to the power of t. This integral of dt will be t. This is your xt, and then we can just open up the brackets and just write like this: a e to the power of at e to the power of t plus c e to the power of t. This is the solution to the differential equation. This is x in terms of t, where a and c are both constants. Now we will move on to the next part. So here we have to consider the case where a is equal to -1. So by differentiating dy by dt equals minus x plus y with respect to t, so that d2y by dt square equals twice dy by dt. So this looks interesting. Let's try to do it. Dy by dt is minus x plus y. Let's try to differentiate it with respect to t. So what we get is d2y by dt squared minus dx by dt plus dy by dt. Yeah, this is what we get. Now one thing here is if we go up, dx by dt is x minus y. Okay, so we can just plug it here in this equation. This would be if we open the brackets, it will be x minus x plus y plus dy by dt. Another thing which we should note here, that the initial equation is minus x plus y equals dy by dt. Here we also have a minus x plus y, so I can replace this minus x plus y with this dy by dt, because these two terms are just same. So it will look like this: dy by dt plus dy by dt. So finally we have proved that it will become twice dy by dt. This is what we were supposed to prove in this problem. Moving on to the next problem. So here we have to substitute y as dy by dt and show that y will be equal to b e to the power of 2t. Okay, that's fine. So y is dy by dt. So basically d of capital Y by dt will be equal to d2 of small y by dt square. Okay, so what happens to this equation? So the left hand side of this equation will become d of capital Y by dt, and the right hand side will become 2 times of capital Y. Now it's a pretty simple integration. A simple integration involved here. We have to integrate both sides. Integrating both sides. Integral of d of capital Y by y is equal to integral of 2 dt. So left hand side will become ln of capital Y. This will be equal to 2t plus c. Again we just have to open it. So c is the constant of integration. So y would be e to the power of 2t times e to the power of c, and we can just assume e to the power c as a constant capital B. This is a constant. So finally what we are left is y is equal to, I can say the capital Y will be equal to b e to the power of 2t. This is what we need to prove in this question, and we have successfully proved it. Now last question, we have to solve for y, which is again not difficult. So capital Y is equal to b e to the power of 2t. So y should be replaced with dy by dt. Now here again it's pretty much a simple integration. It will be integral of dy equals integral of b e to the power of 2t dt. So dy will become y. So this will become b e to the power 2t by 2 plus c, where c is the constant of integration. But in this case what happens is we have to assume that c is equal to 0, because if we do not assume c as 0, our next problem cannot be solved. I don't know why they haven't mentioned this thing in the question, but yeah, here we should assume that b is equal to 0 and y will be this value. This is the answer to this question. Now we have to show that x is equal to minus b by 2 e to the power of minus b by 2 e to the power of 2t plus c. So how to solve this, or how to start? Basically again we have to use the dx by dt equation. So dx by dt is x minus y. So from here we have to solve for x. So dx by dt is equal to x minus y. Let's plug in the value of y. Let's plug in y, which we found out in the previous equation. This will be equal to minus b by 2 e to the power of 2t. Again you can see this is a linear differential equation. So comparing with dx by dt plus p of tx is equal to q of t. We just found that pt is again minus 1, and qt this time is minus b by 2 e to the power of 2t. Now more or less the problem is done. So firstly we have to find the integrating factor. This is e to the power of integral of pt dt e to the power of integral of minus dt, so it will be e to the power of minus t. And the solution of this differential equation will be in this form: 1 by it times integral of it qt plus c. C is the constant of integration, so it would be 1 by e to the power of minus t. This is xt. It is e to the power of minus t. Qt is minus b by 2 e to the power of 2t, ends with a plus c. Now this will become e to the power of t, and here after multiplication, what we would be left is minus b by 2 e to the power of t. And another thing here is we have to take this constant of integration out of the brackets. Yeah, but generally it's taken inside. I don't know why they took it outside. Never mind. So yeah, finally we are with b by 2 e to the power of 2t plus t. This is your xt, and this is what we had to prove in this question, that x is equal to minus b by 2 e to the power of 2t plus c. Now we will be dealing with an advanced case where a is equal to minus 4, and here we have to show that d2y by dt square minus twice dy by dt minus 3y is equal to 0. So it's simple. Again, we have to start with the dy by dt equation. That is, we have to start here, dy by dt, because you have to, I mean, we see terms d2y by dt square on the left hand side, so of course we have to start here. So dy by dt will be equal to minus 4x plus y. I've just replaced a with minus 4 here. Let's find d2y by dt square. Minus 4 dx by dt plus dy by dt. Now we know the value of dx by dt. If we scroll up here, dx by dt was equal to x minus y. Let's put it in this equation. This will be x minus y. This is d2y by dt square. Now just expanding it, what we get is minus 4x plus 4y plus dy by dt. Now again, initially what we see is we can also write it in this way: d2y by dt square minus 4x plus y plus 3y plus dy by dt. It can be written in this way. Why I wrote it in this way? Because I can replace this minus 4x plus y with this dy by dt using the initial equation. Just replacing it here, dy by dt plus 3y plus dy by dt. Now taking them together, d2y by dt square, it becomes twice dy by dt plus 3y. And here comes the last step, d2y by dt square minus twice dy by dt minus 3y equals 0. And if you check the question, this is what we need to prove. Yeah, this question is done. Now in the next question, we have to assume that the solution to this differential equation is y equals f e to the power lambda t, where lambda belongs to r and f is a constant. You have to find two values of lambda that satisfies this equation. So how to do this? Again, it's easy. We have to find out like dy by dt and d2y by dt, plug d2y by dt square and dy by dt and y in this equation, and then solve for the values of lambda. So our y is f e to the power of lambda t, dy by dt will be f lambda e to the power of lambda t, and d2y by dt square will be f lambda square e to the power of lambda t. So we have these three values which we can plug to this equation now. So this will be f lambda square e to the power of lambda t minus 2 f lambda e to the power of lambda t minus 3 f e to the power of lambda t. From these three we can take f and e to the power lambda t as common. So we get lambda square minus 2 lambda minus 3. This will be equal to 0. Now what happens is f e to the power of lambda t, these terms, I mean f is a constant, so f cannot be equal to 0. E to the power of lambda t, this will only be 0 when lambda becomes your infinity, basically. I mean minus infinity. Yeah. So obviously we have to ignore this, and we have to work on this equation to get the values of lambda which satisfies this equation. So lambda square minus 2 lambda minus 3 equals 0. And I believe we can factor this equation. Lambda square plus lambda minus 3 lambda minus 3 equals 0. Becomes lambda times lambda plus 1 minus 3 lambda plus 1 equals 0. So lambda minus 3 times lambda plus 1 equals 0. So the two values of lambda which satisfy this thing, is lambda minus 3 equals 0 and lambda plus 1 equals 0. So lambda equals 3 and lambda equals minus 1. These are the two values of lambda that will satisfy the given differential equation. Okay. Now in the next part, the two values found in part C2 are lambda 1 and lambda 2. Verify that y equals f e to the power of lambda 1t plus g e to the power of lambda 2t is a solution to the differential equation in C1 where g is a constant. So let's plug in the values here of lambda 1 and lambda 2. And let's see what is basically the what is y. So y would be f e to the power of and lambda 1t, so lambda 1 is 3, lambda 2 is minus 1. So 3t plus g e to the power of minus t. Okay, this is y. So let's try to find dy by dt. Dy by dt will be 3f e to the power of 3t, and it's minus g e to the power of minus t. Similarly, we can find d2y by dt square by differentiating it again. So it would be 9f e to the power of 3t plus g e to the power of minus t. Now we have y, we have dy by dt, we have d2y by dt square. Now we have to plug this equation to our initial equation and check if the value turns out to be as 0. So what we need to do is we have to plug this in this equation on the left hand side and check if the value is coming out as 0. If the value is coming out as 0, so LHS will be equal to RHS. So our solution, which we assume, that is correct. So yeah, this is the LHS test. d2y by dt square minus twice dy by dt minus 3y. So d2y is 9f 3 to the power e to the power of 3 plus g e to the power of minus t, minus twice 3f e to the power of 3t minus g e to the power of minus t. Y is minus 3f e to the power of 3t plus g e to the power of minus t. Now we just have to open the brackets and see what happens. This will become minus 6f e to the power of 3t. This will be plus 2g e to the power of minus t. It's minus 3f e to the power of 3t, while the last term would be minus 3 e to the power of minus t. Now see, this 9f f e to the power of 3t will get cancelled by these two terms, and this g will get cancelled by these two terms. So overall it ends up with a 0. RHS is also equal to 0. Hence the solutions are true. This is what we need to do in this step. We have to just verify that the solution is true or not. And yeah, that's the end of this paper. So hope you like this video, and I'll be posting the paper 1 and paper 2 shortly because IB exams are pretty close now. So yeah, also do like this video and do subscribe to my channel. You may also follow me on Instagram. The link is there in the description below. Thank you so much again, and see you in the next video.